In Chapter 10, we're going to be discussing liquids and solids. In this section of Chapter 10, we're going to be talking specifically about intermolecular forces and some properties associated with liquids. So last semester, we talked about the three states of matter, of solid, liquid, and gas. And in our last chapter of our Chem 103 session, we discussed gases. So we're going to start off this semester by talking about liquids and solids. So just quickly to review solids, liquids, and gases on the macroscopic and microscopic level. So remember from last semester, gases on the microscopic level where particles had rapid random motion associated with them, and they had a lot of empty space in between the particles. This microscopic nature caused gases to take the shape and the volume of the container that they were macroscopically in. What we're going to see with liquids is that liquids are packed tightly together, but they do have freedom of motion, meaning that the particles can move past one another in the liquid state, but they're still going to be packed tightly together. This causes the liquid to have a defined volume, but it takes the shape of its container. For our solids, they're also packed tightly together, but they only have vibrational motion associated with the particles, meaning the particles are stuck in space. They cannot move past one another. They can only vibrate where they are at. This causes our solids to have a defined shape and a defined volume. What we're going to see is that the state of a substance is going to depend on the balance between the kinetic energy, or energy of motion, and the interparticle energies of attraction, which we're going to be talking about in this chapter. So let's first talk about the forces that we can have with our substances. The first type of force is going to be an intramolecular force. Intramolecular forces are forces within a molecule, and these forces are what really determine the chemical behavior or the chemical properties associated with any substances. This is what we really focused on last semester. Our intermolecular forces, oftentimes abbreviated IMFs, are now going to be forces between molecules. And these are the forces that are going to determine the physical properties associated with the substance. So they're what's going to help us define whether substances will be in the solid, liquid, or gaseous state at a specific temperature. When we look at our intramolecular forces, these are going to be our bonding forces. So they're going to be very strong in relationship to our intermolecular forces. And in order for an intramolecular force to be present, a bonding force to be present, our atoms have to be very close together. We talked last semester of an overlap of the orbitals within the atoms in order to form those bonds. With our intermolecular forces, these are now just attractions between the molecules, holding them together. And in relationship to our intramolecular forces, they are very weak. The atoms do not have to be as close together. What we're going to see is we're not going to have an overlap of the orbitals when we define the intermolecular forces. So the atoms will be farther apart. If we look at a diagram that helps explain this, we have two molecules. You can think of these molecules as two diatomic molecules. The intramolecular forces, the bonding forces, are shown here with the overlap of the two atoms. They are covalently bound together through that overlap. So this would be our intramolecular force. The intermolecular forces, or the attractive force, is what we're going to see in between our two molecules. And you'll notice that there's no overlap. They're just close together, so there would be an attraction there. When we start talking about the different types of forces, for the intramolecular force, we have the covalent radius and the bond length, which we discussed last semester. For our new intermolecular forces, those attractive forces, we're going to focus on the van der Waals radius, or the van der Waals distance. The van der Waals radius still goes from the nucleus of the atom to where the atom ends so that it can be associated with the next molecule. The van der Waals distance is going to go from the nucleus of one molecule to the nucleus of the other molecule, and the van der Waals radius would be half of that distance. You'll notice from our diagram that the van der Waals radius will always be larger than the covalent radius because the atoms are not going to overlap in terms of their orbitals. So next, let's talk about the types of intermolecular forces that we can have. The first type is going to be our dispersion force. our dispersion force is an attraction between molecules due to an induced dipole. The induced dipole is a momentary dipole due to the movement of the electrons in the electron cloud. So if you remember from last semester, the electrons in the electron cloud are constantly moving. We can never pinpoint exactly where the electron is. We can only say it's in this specific area, hence the orbitals that we focused on. So since the electrons are constantly moving and they have a negative charge associated with them, the induced dipole is a momentary dipole. Remember, dipole, two poles, one positive, one negative side. So all the electrons will conglomerate towards one side of the molecule, making it be partially negative, while the other side of the molecule would be partially positive because the electrons are not in that area. So this is our induced dipole. It's a dipole, two poles, that is a short time frame, and it's only due because of the movement of the electrons. With this induced dipole, we oftentimes refer to these as London dispersion forces. It causes a polarizability within the molecule because at any one point in time, the electrons may be on one side of one molecule, causing it to be partially negative. So if we look at our diagram here, remember our notation, we have our partially negative side, which is where the arrow is pointing, and it's where the electron density is. The other side of our molecule is partially positive. And again, this would be a momentary fraction of time, but it will influence a molecule that is close to it. And that molecule that is close to it, the negative side is going to repel the electrons in that molecule and push them farther away, leaving an attractive force between the partially negative and the partially positive side of the other molecule. One of the things to remember with these types of forces, they are intermolecular forces between molecules. So we're going to use these dotted lines between molecules to show that attractive nature that we would have. So an example of a dispersion force would be between two fluorine molecules. At any one point in time, the electrons will conglomerate on one side of the fluorine molecule. So we can denote that with our partially negative and partially positive signs, which will then influence the adjacent molecule to assign the similar notation, partial positive, partial negative. So the partial negative and the partial positive side of two different molecules can be attracted to each other. This is our dispersion force. It's a momentary force in between molecules due to the movement of our electrons. With our dispersion forces, they are going to be present in all types of molecules because all of our molecules have electrons, and those electrons are always free to move. So it's found in everything. But it's going to be the only force that is found in our nonpolar molecules. So you want to make sure that you can recognize when a molecule is nonpolar and when a molecule is polar based on its shape and the atoms it contains. Dispersion forces will be present in everything, but they're the only force present in nonpolar molecules. The strength of our dispersion forces is going to depend on the polarizability of the molecule. Polarizability is defined at the ease with which an electron cloud of a particle can be distorted, meaning the ease in which we can force the electrons to one side of the molecule compared to the other to cause that momentary dipole moment. So polarizability is going to increase with increasing molar mass. So as we increase the volume and the number of atoms, we increase the molar mass, it becomes more polarizable. Cations are going to be less polarizable than anions. Remember, cations are smaller than their parent atom, so they're harder to polarize, while anions are larger than their parent atom, so they're going to be easier to polarize. So looking at just a diagram or a model where we can see some differing atom sizes, we can talk about their polarizability, and we can base this on boiling point. So one of the things that we want to be able to do with these dispersion forces is any of these intermolecular forces help us explain physical properties, so things like boiling points. So we want to be able to apply these forces to some of those properties. So what you're going to see here is our boiling points are going to increase, which means it's going to take more energy to pull the molecules apart or to break those intermolecular forces and go into the gas phase. Remember, the gas phase, we said, had no attractions between molecules because the molecules were so far apart. So boiling point is a good indicator of how strong our forces are between the molecules. The stronger the forces, the higher the boiling point. So what you'll notice in our diagram is that the larger our molecules become, the more polarizable they become, the higher the boiling point, because the stronger those dispersion forces will be. You'll notice it's the same where we have our monatomic gases there in column 18 versus our diatomic gases there in column 17. The diatomic gases are going to be much larger in their molar mass and size because it contains 2 atoms. So once again, their boiling points are going to be much larger than the monatomic gases in the same row. So that is one of the applications that you'll want to be able to do with all of these forces, is be able to apply them to some of the physical properties that we'll be discussing. So since dispersion forces depend on the molar mass and polarizability, we also need to talk about what's going to happen when we have molecules that have similar molar masses. And when we look at things that have similar molar masses, we're going to look at the molecular shape to help us determine the strength of the dispersion forces. And if we have molecules with the same molar mass, the more surface area we have, the larger those dispersion forces are going to be. So I'm going to give you an example of 2 molecules that both have the formula C5H12. So these would be isomers of each other. They have the same formula and therefore the same molar mass. But we can actually draw our structure of C5H12 in 2 different ways. So the one in the top is what we call N-pentane, where we connect all of the carbon atoms in a chain with the hydrogen atoms. The one underneath is neopentane, and this is where we have 1 carbon in the center of our molecule, and the other 4 carbons are all attached to that central carbon atom. So they have very different shapes. The one on the top I like to refer to as a hot dog. It's this very long chain, while neopentane is more like a sphere. So when we look at the surface area that we would have between our 2 molecules, it is very different. N-pentane has a lot of area between the 2 molecules because of the chain, while neopentane only has a small surface area between the 2 molecules because of its spherical shape. So this is going to impact our dispersion forces, and you can see that based on the boiling point. Even though they have the same molar mass, their boiling points are very different. N-pentane has a higher boiling point than neopentane because of the surface area. The more surface area, the more energy it's going to take to break those 2 molecules apart into the gas phase. Compared to neopentane with a small surface area, it will not take as much energy to make it go into the gas phase. So when molecules have similar molecular masses, we want to look at the shape. The more surface area we have between our molecules, the stronger the dispersion forces will be. Our next type of intermolecular force is going to be dipole-dipole force. These are attractive forces between the positive end of one polar molecule to the negative end of a second polar molecule. And what we're going to see with these is that strength is going to increase with increasing polarity for molecules of equal mass and size. So this is where we're now going to have a permanent dipole. So these will be found in our polar molecules. So you'll notice now this molecule has a permanent partially negative side and a permanent partially positive side. And they're going to line up in such a way that the negatives and the positives will be attracted to each other when we have them in the liquid state. So an example of this in diatomic terms would be a molecule between iodine and chlorine. Chlorine is more electronegative, so it has the partially negative side. Iodine would be our partially positive side, and this is permanent due to the electronegativities. So they're going to line up in such a way that the chlorines and the iodines are attracted to each other based on their polarities. The stronger the polarity, the stronger the intermolecular force. A third type of intermolecular force is going to be hydrogen bonding. I absolutely hate this term because it is not a bonding force per se. It is just an intermolecular force, an attractive force between structures. But it is referred to as hydrogen bonding because of its strength. And this is the attraction between a hydrogen that is bound to oxygen, nitrogen, or fluorine, so a very polar bond, in one molecule, and it's attracted to the non-bonding electron pair on an oxygen, nitrogen, or fluorine in another molecule. So since we're looking at a very polar bond, this is just a special type of dipole-dipole force. It is a special type of force because of how strong the hydrogen bond is between the 2 types of molecules. So what we're looking at here in our example is we have the hydrogen that is highly partially positive when it is attracted or it is bound to an oxygen, nitrogen, or a fluorine. Because remember, nitrogen, oxygen, and fluorine are some of our most electronegative atoms. That hydrogen atom, because it is so partially positive, is highly attracted to the lone pair of electrons on another oxygen, nitrogen, or fluorine in a different molecule. So we're still talking about two different types of molecules. Water is one of the best examples of hydrogen bonding. The hydrogen in one water molecule is highly attracted to the lone pair of electrons on the oxygen atom in a second water molecule. All of these forces are going to be additive, and molecules can contain more than one type of force. Remember, dispersion forces are found in everything. All substances contain dispersion forces, and it's usually the force that contributes the most to the overall attractive force between the two molecules. So we do want to be able to compare the different types of forces, or how strong molecules are attracted to each other based on the types of forces present. So for comparison guidelines, molecules that have similar molecular weights and shapes, the type of intermolecular force is going to determine the strength. So dispersion forces are the weakest in terms of all of our forces because they're only due to that momentary dipole, while our hydrogen bonding is the strongest force because of how polar the hydrogen is and its attractive nature to the lone pair of electrons. So when molecules have similar molecular weights and shapes, we're really just going to compare the type of force. The stronger the force, the stronger the intermolecular forces within the substance. But if our molecules have very different molecular weights, the dispersion force is really going to determine the overall strength of the force between the molecules. So then we would just be comparing the dispersion forces between one molecule set and another. So next, let's talk and review about some of the properties associated with the liquid state. What property is going to be the viscosity of a liquid? Viscosity is defined as the resistance of a liquid to flow. So this is going to depend on the attractive force between the molecules as well as the shape of the molecules. The higher a substance's viscosity, the less it is going to flow. So if we look at these 5 test tubes, the one here on the right has the higher viscosity. The liquid is really not flowing out of the test tube very easily or very quickly. So it has very strong attractive forces, and the shapes of the molecules are probably also very large and very branched. While the one here on the left has a very low viscosity because it is flowing out of the test tube very, very easily. Another property that liquids show is going to be surface tension. Surface tension is the energy required to increase the surface area of a liquid by a unit amount. And it is most evident in liquids than it is in any of our other states of matter. This is due to an imbalance in the intermolecular forces at the surface of the liquid compared to the intermolecular forces in the center of a liquid. So if we look at a beaker, and if we look at a liquid, a molecule that's in the center of our liquid, it has molecules completely surrounding it. So it has forces completely surrounding it in 360 degrees. So it's being pulled the same strength in all directions around it. But if we look at a liquid or a molecule that's at the top of our liquid, it only has other liquid molecules underneath it and beside it. There are no particles above it for those forces. So its net directional force is going to be downward into the center of the liquid. And that's what causes our surface energy and our surface tension. So the more energy would be required to increase the surface area by a specific unit amount is going to be based on those intermolecular forces and the strength of them at the top. The stronger the intermolecular forces, the stronger the surface tension. Another property is going to be capillarity. Capillarity is the rising of a liquid through a narrow space against gravity. We have a couple of different forces here that help with capillarity. One is going to be cohesive forces, and these are when molecules are attracted to one another. Another force we're going to see is going to be adhesive forces, and these are when the molecules are attracted to a surface instead of each other. So if we look at 2 examples for cohesive and adhesive forces, figure A here on the left, where we have water in a test tube, and it's showing our meniscus. So this is one of the things that we have to watch for in the lab is that meniscus. And this is going to be due to adhesive forces. The water molecules are attracted to the surface, the glass, that we see in our glassware. So we see this curve upward, which is what causes our meniscus, due to the attractive nature between the molecule and the surface. So these would be our adhesive forces, and very strong adhesive forces. Cohesive forces are the opposite. These are when molecules are attracted to one another instead of the surface. So in structure B that we see here, we now have mercury in our glassware. And mercury, since it has different intermolecular forces than our glass does, is more attracted to itself than to the glass surface. So these would be our cohesive forces. And what we'll see with capillarity is an alternating of these forces as a liquid walks up whatever its narrow space is. So the capillary tube, if we were in the lab, and liquid rising in a capillary tube. We see an alternating adhesive and cohesive forces until our liquid gets to a height where one of these forces completely outweighs the other, whether that be the adhesive force that we see with water in glassware or the cohesive forces like we see with mercury in our glassware. We can actually determine the height a liquid will rise in a capillary tube through this equation. H equals 2t cosine of theta over r rho g. And we can use this equation to determine how high a specific liquid will climb in a capillary tube. In this equation, H represents the height of the liquid in the tube relative to the liquid outside of the tube. T here represents our surface tension of the liquid. So that was the previous property that we looked at. Our unit for surface tension is newtons per meter, where Newton is our unit of force and meter is our unit for distance. So surface tension is measured in the units of Newton per meter. This surface tension is going to be liquid specific. So this is the variable that will really define for us the liquid that we are using. Theta is the contact angle between the liquid and the tube. This is typically 0 when the material is attracted to the tube. So this would be like using water in one of our glass capillary tubes. R is going to be the radius of the tube that we're dealing with. Rho is going to be the density of our liquid. So once again, it will be liquid specific for us. And G represents gravity, which is equal to 9.8 meters per second. So we can use this calculation to determine how high a liquid will go in a specific capillary tube. The surface tension for water is equal to 71.99 millinewtons per meter. So this becomes a constant that we can look up for any of our substances. We will typically be doing things with water, so the surface tension for water is 71.99 millinewtons per meter.